Hi everyone. So in this video we continue with chapter 8, complex numbers, and now into section 8.3, powers and roots of complex numbers. So let's take z as a complex number in the trigonometric form, r times cosine of theta plus I times sine of theta. Then z squared would be the same as multiplying z times itself, and then we expand that. Well, notice that we group r squared, but then expand the rest through the distributive property. And notice that we end up with this expression here. So r squared times cosine squared minus sine squared of theta plus I times 2 sine of theta cosine of theta. But these are double angle identities. This one is a double angle identity for cosine, and this is the double angle identity for sine. So we end up with r squared cosine of 2 theta plus I sine of 2 theta. Then if you multiply z squared by z once again, and you expand and all that, this step is not here, but you would get the equivalent of an angle sum identity. In this case, theta plus 2 theta for both cosine and sine. So then we end up with r cubed cosine of 3 theta plus I sine of 3 theta. So in general, you have a pattern. And from this pattern, you obtain a theorem, which is named after the French mathematician Abraham de Moivre. So here we have de Moivre's theorem. And basically what it says is that to find the nth power of any complex number written in trigonometric form, we take the nth power of the modulus, which you can see here, and multiply the argument by n. Now here's the proof, which I suggest you study carefully because it's a beautiful example of using the method of induction. So we start off with example 8.18, and they want us to find 1 plus I to the power of 6. So the first thing you want to do is convert the number from Cartesian form into polar form. That's what you can see here in this step. We did this one in the previous example, and we found that the modulus was square root of 2, and the argument is pi fourths. And all we have to do now is apply de Moivre's theorem. So this to the power of 6 is going to be equal to this to the power of 6. So we grab the modulus to the power of 6 and multiply the arguments times 6. And we end up with 8 times cosine of 3 pi halves plus I sine of 3 pi halves. But remember that cosine of 3 pi halves is 0 and sine of 3 pi halves is negative 1. So we end up with 8 times negative I, or negative 8i. So now we're going to take a look at uses of de Moivre's theorem in problem solving. And let's just start with this expression right here. Z to the minus 1 is going to be, again, this to the power of negative 1, and then multiplying the argument by negative 1. And then we end up with this expression, 1 over r times cosine of theta minus I sine of theta. This is similar. They're using the same property that we just found here, but now making it to the power of n. And you end up with r to the minus n, and obviously multiplying the argument by negative n. Now they're missing one step here because this would equal 1 over r to the n. And this is the same as cosine of n times theta minus I sine of n times theta. So if we take the case where r equals 1, the modulus equals 1, then z to the n would simply be cosine of n times theta plus I sine of n times theta. Then z to the minus n is going to end up equaling this, cosine of n times theta minus I sine of n times theta. So notice that if we add z to the n plus z to the minus n, you'll end up with 2 times cosine of n theta. That's just from adding this and this. And if we subtract it, we're going to end up with 2i sine of n times theta. So these relationships are quite helpful in allowing us to write powers of cosine of theta and sine of theta in terms of cosines and sines of multiples of theta. So we continue with example 8.19, and it says find cosine cubed of theta in terms of first powers of the cosine function. So for this, we start with using this expression here, z plus 1 over z is equal to 2 times cosine of theta. Now, where does this come from? Well, remember that we said that z to the power of n plus z to the power of minus n is equal to 2 times cosine of n times theta. So this here is equivalent to z to the 1 plus z to the minus 1. So that's why these expressions are equivalent, because this would simply be 2 times cosine of theta. So we expand the left-hand side, and notice that we get this expression, right? This is a normal binomial expansion. Then what we can do is that we group. Notice that we have z to the 3 here, and we also have it here, so we can put it together. Z to the 3 plus 1 over z to the 3. And we do the same thing with 3z and 3 times 1 over z. We factor out 3, and in parenthesis we get z plus 1 over z. But we already know that this expression here is going to equal 2 times cosine of 3 theta, right? Because this is simply z to the 3 plus z to the minus 3. So it equals this. And this one equals this, 2 times cosine of theta. And because we also expanded the right-hand side where we got 8 times cosine cubed of theta, we need to solve for cosine cubed of theta, but that's simple. Simply multiply both sides by 1/8, right? That's where we get this cosine cubed of theta is equal to 1/8 times this other expression, and we end up with 1/4 times cosine of 3 theta plus 3 cosine of theta. So now we have example 8.20, and it says find formulae for cosine of 3 times theta and sine of 3 times theta in terms of sine of theta and cosine of theta. So for this, we're going to use a different approach. First, we're going to use De Moivre's theorem. Notice that if we have cosine of theta plus I sine of theta to the power of 3, that is simply equal to cosine of 3 theta plus I sine of 3 theta. Now, here we're going to apply a normal binomial expansion, or using Pascal's triangle, and we get this expansion here. Then what you do is that you group the real part and the imaginary. The imaginary is just those that are in terms of I. Now this is I squared, so this is -1. That's why you end up with this here, -3 cosine of sine squared. And then I cubed is the same as I times I squared. And I squared is just -1, which we see here. And we factor out the I in both this case and that other case, right? What I mean by this case and that case, I mean this case here and this one over here. So now all we have to do is compare the real part and the imaginary parts. So that means that cosine of 3 times theta is going to equal this expression, which we got from here, and then sine of 3 theta is equal to this expression, which we got from here. So next we have example 8.21, and they ask us to simplify this expression. Notice that it says cosine of 6 theta plus I times sine of 6 theta. Now this part can be, using the inverse of De Moivre's theorem, can be rewritten as cosine of theta plus I sine of theta to the power of 6. And in similar fashion for this part and this part, we can rewrite them as cosine of theta plus I sine of theta to the 3, and this divided by cosine of theta plus I sine of theta. to the power of 4. And then this just becomes a problem of adding and subtracting exponents because we have the same basis. So we end up with cosine of theta plus I sine of theta to the power of 5. And this, of course, is the same as cosine of 5 theta plus I sine of 5 theta. So now we're going to talk about nth roots of a complex number. And de Moivre's theorem is essential for finding nth roots of complex numbers. Now, from example 8.18, remember that 1 plus I to the power of 6 is equal to negative 8I. Now, what that means is that 1 plus I is the sixth root of negative 8I. Why? Well, because this to the power of 6 equals negative 8I. Another example, if W equals negative square root of 3 plus I, this is the 10th root of 512 plus 512I square root of 3, because negative square root of 3 plus I to the power of 10 is equal to 512 plus 512I square root of 3. So to find the nth roots, we can apply the definition of an nth root. So let W equal S times cosine of alpha plus I sine of alpha be the nth root of Z equals R times cosine of theta plus I sine of theta. So this means that W to the n is equal to Z. In other words, this expression to the power of n should equal this. Then from here, we obtain this equality, right? Applying de Moivre's theorem, S to the n times cosine of n times alpha plus I times sine of n times alpha is equal to R cosine of theta plus I sine of theta. So from here, because two complex numbers are equal only if their moduli are equal, then we have that S to the n is equal to R. So S is equal to the nth root of R, or R to the 1 over n. We also have, from this other part of the equality, that cosine of n times alpha is equal to cosine of theta, and that sine of n times alpha is equal to sine of theta. Now recall that both sine and cosine are periodic functions with a period 2 pi. Hence, from this relationship, we get that n times alpha is equal to theta plus 2k pi for k equal to 0, 1, 2, all the way to n minus 1. So this leads to this. Alpha is equal to theta plus 2k pi divided by n. And we can separate this into two expressions. Theta divided by n plus 2k pi over n for k equal to 0, 1, 2, 3, all the way to n minus 1. Summarizing, what we have is this. If z is equal to r times cosine of theta plus I sine of theta, and n is a positive integer, z has n distinct nth roots. So this is the formula for finding all the n distinct roots. So it's going to be the nth root of r. Now notice that this is z sub k. And we're going to start with k equals 0, not 1, as it says here. So 0, 1, 2, 3, all the way to n minus 1. So what this means is that depending on the nth root, you will have that many solutions. And each one of these solutions is given by this formula. So it's r, the nth root of r, times cosine of theta over n, plus 2 times k pi over n, plus I sine of theta over n, plus 2k pi over n, again with k from 0 to n minus 1. So now let's apply this to example 8.22, where they ask us to find the cubic roots of z equals negative 4 square root of 2 plus 4i square root of 2. So the first thing we have to do is find the modulus and argument for this complex number. So notice that the modulus is 8 and the argument is 3 pi fourths. So then we use the formula, W equals S times cosine of theta over n plus 2k pi over n plus I sine of theta over n plus 2k pi over n. So all we have to do is substitute. We take the third root or the cubic root of 8 for the modulus, and then we have cosine of 3 pi fourths over 3 and the rest of it, right? So we end up with this expression, and now all we have to do is substitute k for the values starting from 0 to 2 because 2 is n minus 1. And then all we have to do is substitute k for 0 and we get this for W1. For W2, we substitute k with 1 and we get this expression. And then we substitute k for W3. We substitute k with 2 and we get this expression. So now look at the roots here in the complex plane. The first expression we found had modulus pi fourths, and that's represented by W1. Notice that they form a circle because they have the same radius or the same distance from the origin, which was the third root of 8, which is 2. So there's 3 solutions that we found, and notice that they have the same difference between them, which is 2 pi thirds. So notice that this distance here is 2 pi thirds, this is 2 pi thirds, and this is also 2 pi thirds. Now, notice that if we go beyond k equals 2, we would get back to W1. So the cycle just repeats. So we continue with example 8.23, and it says, find the sixth roots of z equals negative 64 and graph them in the complex plane. So z equals negative 64. Where is this number? If you think about the complex plane, it's over here, right? Negative 64. So that means that r is going to be 64, and the angle theta, or the argument, will be pi. So then we can write, using the formula, the roots in this form here, right? Because we would do the sixth root of 64, which is 2, and then pi over 6 plus k pi over 3 for both cosine and sine. And now all we have to do is plug in the values for k starting 0 through 5, which would be a total of 6 roots. So here we have all the solutions, W1, 2, 3, 4, 5, and then the next page you're going to see the solution for number 6. So here is W6, and here they are represented on the complex plane. Notice that the first argument we found was pi over 6 for W1. Obviously this distance here is the modulus, or 2. And then each one of them has a difference between them of pi thirds. So this distance here is pi thirds, pi thirds, pi thirds, pi thirds, pi thirds, and pi thirds. And we have a total of 6 solutions. So next we have the nth roots of unity. The rules we established can be applied to finding the nth roots of 1, which is unity. Since 1 is a real number, in polar form it has a modulus of 1 and an argument of 0. So we can write it in the form 1 equals 1 times cosine of 0, which is 1, plus I times sine of 0, which is 0. Then we can apply the rules from before, and 1 has n distinct nth roots that is given by the formula we saw previously. So notice that once you do 0 over n, this just cancels out, and we end up with this expression here. Obviously, the nth root of 1 is always going to be 1. So cosine of 2k pi over n plus I sine of 2k pi over n, with k equal to 0 all the way to n minus 1. Or in degrees, 360 degrees times k over n for both cosine and sine. So next we have example 8.24, and they say find part A, the square roots of unity, and part B, the cube roots of unity. So this is fairly simple, right? It's just a matter of applying the formulas. So in the case of the square root of unity, we know that k equals 2. So all we have to do is substitute for, well, actually n equals 2. This is n. So all we have to do is substitute for k with 0 and 1. And notice that for z sub 0, we're going to get cosine of 0 plus I sine of 0, and that, as we know, is equal to 1. And then we would have 360 times 1, right, over 2, so 180 degrees, and that's going to end up being negative 1. For the cubic root of unity, now this should equal n here, should say n, then the three roots would be determined, and in this case they're using not the 360 degrees, but rather 2 pi, as you can see here. So it's the same thing, but in radians. So we use k equals 0, 1, and 2, not 3 here. This is a 2. So all we would have to do is substitute with those values for k and just plug in the formula, and we get the results. 1 minus 1/2 plus I square root of 3 over 2, and minus 1/2 minus I square root of 3 over 2. So in the next slide, you're going to find a title that says Euler's Formula. The following results are proved in Chapter 16. Taylor's or Maclaurin's series expansions for sine of x, cosine of x, and Euler's number to the power of x are the following. So notice that sine of x is going to equal x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so forth. So this is an infinite series, and here you have it in sigma notation. So this is from 0 to infinity, negative 1 to the n, so that's why we have the alternating signs. Notice that you have plus, minus, plus, minus, plus, minus, and so forth. And then you would have that the fraction is x to the power of 2n plus 1. So this is the definition of an odd number. So notice that we have an odd exponent successively. Now for cosine, you have the same thing, but in this case, it's going to be even numbers for the exponents and also for the factorial in the denominator. And this is the sigma notation of the series. Now e to the x is very interesting because in this case, you have a sequence that follows the natural number starting with 0. So notice that it's just 0, 1, 2, 3, 4, and the denominators are 2 factorial, 3 factorial, 4 factorial. So ideally, we must find, or we could probably find a way to combine these two and get this. So in the next page, we have sine of x plus cosine of x, and it's just a combination of those two series that we saw. And notice that now we would have the even terms as well as the odd terms. But there's a problem, and that is that you have alternating signs here still, whereas e to the x did not have alternating signs. But that can be solved using I, because I follows a very interesting sequence. With I, you get, I is just I squared is negative 1, I to the 3 is negative I to the 4 is going to be 1, I to the 5 is going to be I again, I to the 6 is going to be negative 1, and so forth. So it follows a sequence. So we could use this sequence, and notice that if we have e to the power of I times x, the expansion of that would include these terms for I. So we would have I to the 0, I to the 1, I squared, I to the 3, I to the 4. So this will give us a solution that is going to have the alternating signs that we need. And it turns out that e to the power of I times x is going to equal cosine of x plus I sine of x, because if we factor the i's, as we can see here, this is going to be the same expression that we had before for the expansion of sine of x, and this part in red is going to be the same expression for the expansion of cosine of x. So for any complex number, it follows that we can express e to the I times theta as being equal to cosine of theta plus I sine of theta. And this is known as Euler's formula. So now we have example 8.25, and it says evaluate each complex number. Part A, e to the power of I times pi. So this is going to equal cosine of pi plus I sine of pi. So cosine of pi is going to be -1, and this is going to be 0. Therefore, e to the power of I times pi is equal to -1. And then for b, we have e to the power of I pi halves, and this is simply going to be cosine of pi halves plus I sine of pi halves. But cosine of pi halves is 0 and sine of pi halves is 1, so this just equals I. So next we have example 8.26, and they ask us to use Euler's formula to demonstrate De Moivre's theorem. So De Moivre's theorem, remember, is R times cosine of theta plus I sine of theta to the n. And we know what this equals, but we have to use Euler's formula to demonstrate it. So we can just rewrite this using Euler's formula. Notice that this would be R times Euler's number to the power of I times theta, and this to the n. And then from the rules with exponents, we would have that this is equal to R to the n times e to the power of I times n times theta. And this is simply going to be R to the n times cosine of n times theta plus I times sine of n times theta. So now we have example 8.27, and it says find the real and imaginary parts of each complex number. So letter A says z is equal to 3 times Euler's number to the power of I times pi over 6. So notice that the modulus of z is 3, and the argument of z is going to equal pi sixths. Now, this means that the real part of z is simply going to be 3 times the cosine of pi over 6. And this is 3 square root of 3 over 2. And the imaginary part of z is simply going to be 3 times the sine of pi over 6. And this is going to equal 3 halves. For part B, we have z is equal to 7 e to the power of 2i. Now here, the modulus of z is 7, and the argument of z, in this case, is 2. So that means that the real part of z is going to be 7 times the cosine of 2, and we'll leave it here in exact form. And the imaginary part of z is going to be 7 times the sine of 2. So now we have example 8.28, and it says express z equals 5 plus 5i in exponential or Euler form. So basically what we need, first of all, is the modulus, which we know in this case would be the square root of 25 plus 25. That's the square root of 50, which is going to end up being 5 square root of 2. And the argument of z is going to be the inverse tangent of 5 over 5, right? Which is 1. So this is just pi fourths. Therefore, z is going to equal 5 square root of 2 times Euler's number to the power of I times pi fourths. So in example 8.29, they want us to evaluate the previous number to the power of 6 and express the answer in Cartesian form. So what we're going to do is use Euler's form of the number, and notice that this would be the same as saying 5 square root of 2 times e to the power of I times pi fourths, and this to the power of 6. So recall that this would be 5 square root of 2 to the power of 6, and that's 125,000. And Euler's number to the power of I times pi, 3 pi halves, 3 pi halves. So notice that this is the same as saying 125,000 times cosine of 3 pi halves plus I sine of 3 pi halves. But cosine of 3 pi halves is 0, and sine of 3 pi halves is -1. Therefore, this equals -125,000 I.